Discuss the proof then in the context of a toy model. I had this lemma I was describing, but I think I'll describe that later about the mutability of the coloring.
So what proof are we talking about?
Okay, so this is the proof of Wise's conjecture. So we're starting with a cube complex. I'm actually just going to, for the pictures, I'm just going to draw the cube complex I had here, which already has embedded hyperplanes, but you can still apply the proof. Just forget that they're embedded and apply the logic of the proof and see how it goes. So, so we have this cat-0 cube complex, and so the first step then is to construct an infinite sheeted regular cover, this X here, where the hyperplanes, which are in this case these curves, are compact, so they remain curves. And this follows, okay, so I didn't describe this in the other talk, on the other slides, but applying what I call weak separability. So this is the step which I make use of the Malnormal special quotient theorem, and depends on all of Donnie Wise's work. So weak separability is a kind of condition where you have a subgroup of a group, or maybe I can go back and state the weak separability condition on here. Sorry, this is from a different talk that I gave, or did I describe? I think I have weak separability here somewhere. Sorry about this. Well, I don't see the definition. Okay, well, so what, in the appendix to my paper, Groves and Manning and I show that if G is a hyperbolic group and H and G is a quasi-convex virtually special subgroup, so you should think of G as a fundamental group of a cat-0 cube complex of dimension n, and H is the fundamental group of a component of the hyperplane complex that's, by induction, is virtually special, then H is weakly separable in G. What weakly separable means is that for any element that's not in H, I can find a homomorphism of G to a group. That group might be infinite, but the image of H in that subgroup is finite, and it's separated from that element in that finite subgroup. So it turns out from this Malnormal special quote.
H is finite?
The image of H is finite.
And the element is separated from H. The image
in the image.
In the image.
Yeah.
It's not in that finite.
It's, right. So the proof of this makes use of what I was saying before, the hyperbolic Dane filling, as well as a method of so-called height reduction for quasi-convex subgroups, which is developed in our previous work from 2008. And the Malnormal special quotient theorem of Donnie Wise. So I was going to take this as sort of a black box, but it's a huge black box that, so what does it mean in this case? Well, you can get this covering space with embedded walls. So when you have walls that cross, in the universal cover, the walls of a cat-0 cube complex are all nice and embedded, and these nice embedded hyperplanes. If they cross downstairs, that means there's a covering translation that sends a hyperplane to cross itself. So what you use separability for is you can, any of those elements that make a hyperplane cross itself, you can separate that from the hyperplane subgroup, and you can get a covering space in which that element that was forcing them to cross no longer forces them to cross in the covering space, and then you get it to be embedded. So you do this for, there's only essentially finitely many elements that cause it to cross itself up to some equivalence relation. And so you separate those elements from the subgroup, and you get a covering space where things don't cross. But remember, it's only weak separability. So this covering space has the property, because the image of this subgroup is finite in the quotient. When you pass to the covering space, the wall you'll have only taken a finite sheeted cover of the wall in the covering space. You've removed that self-intersection, but now you've passed to an infinite covering space. So but using this sort of separability argument, then you can get this infinite covering space where all the walls are still are compact. So, and they don't cross, yeah. So,
Compact.
because use the weak separability. So the weak separability condition says that the subgroup in the quotient group has finite image. So when you pass to the kernel of that homomorphism, that subgroup will pass to a finite-sheeted cover. It will have infinitely many components, but each component will be compact.
Compact.
That's right, because it's a compact cube complex. So actually in this example here, then we want a covering space of this surface that has the property that all these circles are compact, so they're still circles. And here's a picture of what this can look like. But think of this as a Euclidean plane with all these holes punched through it, and take two copies of it, sort of thicken it up. And these red circles then will double to form the circles that you see here. So it's really, I'm taking sort of the universal cover of one of these pairs of pants with blue circles, and then everything is sort of doubled. And this is our sort of a schematic of what this covering space could look like. And in fact,
Things are also circles.
red things are also circles, but I've only drawn half of them. Yeah. And in fact, this comes from the homomorphism of your group, where I kill the third powers of each of these elements. And actually, I'm killing each of these guys. So these guys actually lift. If you kill the third powers of these, you get the 3, 3, 3 triangle group. And so that's why you see this Euclidean picture here. So each of these guys. So that's just, I mean, in general, it's going to be much more complicated than that. Just so I can draw it, this is what the covering space might look like. So now all the walls are embedded up here. And so if I color the walls different colors, then I get a hierarchy of this covering space. And it's finite stage hierarchy because you can color with finitely many colors. But at the end, at the terminating step, or each step in between, you're going to have an infinite thing. Obviously, you started with something infinite, but in the end, you get these compact things, which are just stars of the vertices of the cube complex. So here's what I was defining before. So you take this crossing graph of this infinite complex script X, and you take a graph where the vertex set of the walls, or the hyperplanes of that complex, and you have an edge between those if they intersect, or if there's an essential cylinder going between them, which represents that the two subgroups intersect non-trivially up to conjugacy. So then we define the coloring space of this graph. Cn of gamma is the space of colors of the vertices of the graph. So if you have vertices at that are endpoints of an edge, then they have to have different colors. And that corresponds to when you make the hierarchy, you want to make sure that when you cut along the hyperplanes, you're not cutting along hyperplanes that are crossing at a given stage. You cut only one hyperplane at a time. Then,
How do you know there is a color?
Because it's a finite valence graph. So yeah, so I'll describe that in a second. Or when you have a finite valence graph, say if the valence is bounded by k, then you can always color with k+1 colors, because you just color some vertex, whatever color you want, and then you just do it by induction. So by you ordering the vertices. So each vertex will be adjacent to k vertices. So you always have one color available if you use k+1 colors.
Vertices, and then
Yeah.
in the order,
One by one.
and just whatever's ruled out, pick a different color.
Yeah. There's a cool theorem that I think, let's see, you can actually do it with k colors, unless there's like a complete subgraph or something. I forget the theorem, but anyways, it doesn't really matter for this purpose. Okay, so we can regard this as a closed subspace of the Cantor set, just the power, the colorings. We can regard this as the colorings of all the vertices. That's a compact set, and so we have all these closed conditions, so it's a closed subset. So if the degree of the graph is less than or equal to k, then there'll be a non-trivial k plus 1 coloring. So this will be a non-empty subset. So a coloring gives rise to a hierarchy of the complex. So you take your cube complex, and you have all these hyperplanes, which are drawn here, and then you cut them along these hyperplanes one at a time. And what's left at the end are just stars of the vertices. And you have the residues of the colors sort of remaining on the boundaries. That was this Rubik's Cube picture that I had earlier. So
So for each vertex you have
A bunch of half cubes, shall we call them?
yeah,
Whatever.
that's exactly right, yeah.
The faces are colored.
And they've got, yeah, so you keep track of the colorings that they had on the faces, and which tells you sort of what order things were cut up in. Okay, so then the claim is that there exists a probability measure on the space of k plus 1 colorings, which is invariant in the group of automorphisms of this graph. In fact, it's defined. You define it without. Yeah.
So the picture had different colors on different faces.
Yeah.
So these,
Well, I haven't drawn the colors in this picture.
I know, but each blob at the vertex gets one color.
So the hyperplanes, so the vertices of the graph, this crossing graph, correspond to hyperplanes of the cube complex. This cube complex here. So here I've colored it actually in just two colors. I've colored red and blue. So I have a hierarchy here where I first say cut along the red hyperplanes, and then I cut along the blue ones. And that's a two-stage hierarchy. And what I end up with are all these hexagons.
On to what?
The vertices are not drawn in this picture. They're the vertices of the dual cube complex. So here I've drawn the hyperplanes. Here are the vertices of the cube complex. They're in the centers of these hexagons. And the stars of the vertices will just be these hexagons here. So here I haven't drawn the vertices, but but when I cut along the walls, I'll be left with these cubical polyhedra, which are the stars of the vertices. So they're made of these half cubes, as John says.
So it's like you have a cube complex and then sort of the dual object. Just going through the walls, that's this graph.
That's right. There are these hyperplanes that
What?
the graph is obtained by, you have a vertex for each hyperplane. And if two of these hyperplanes cross, then there's an edge between those the corresponding vertices.
Oh, that graph. Oh, the crossing graph.
So, yeah.
Oh, yeah.
So like the graph here, you'd have a vertex for each of these blue guys, and then you'd have a vertex for each red one, and then there'd be an edge between them. I didn't actually draw the graph in this case, because you can just draw the hyperplanes, but...
But you're more interested in this picture.
Yeah, that's right. The graph is just encoding this information, yeah.
So the vertices would be the midpoints of these hexagons,
That's right.
and
The vertices of the cube complex.
then this surrounding thing is
Yeah, so they correspond to these vertices.
with six faces alternately red and blue.
Right.
So where are the squares or cubes here?
I didn't draw them, so they're
Just do it with your finger.
the lifts.
Picture.
They're the lifts of these guys. So there's a
See a cube.
so I smashed things down so that there's a vertex in the middle of each of these hexagons, and the edges go over this blue edge and then up to the other sheet. There's actually two copies of this that make the cover, which I smashed together.
Where's a cube or a square or something?
So the cube, so here's a cube. I go this edge, then I go around the back, then I go that edge, and then I come back here. So that corresponds to here I have a
Square then.
that's a square. It goes there, back around, and then there. And that's
A two-dimensional cat zero.
two-dimensional cat zero, yeah.
Okay.
Actually, this theorem I knew how to prove in like 2011 using for two-dimensional square complexes that were cat minus one. but it took me a while before I was able to do the general case, because Johnny Wise's theorem wasn't, he had to generalize it a little bit. Anyways, it's the two-dimensional case is a little bit easier for certain technical reasons, mainly because the walls in that case are graphs, and so we already know that they're virtually special, and you can use hyperbolic Dane filling to fill them in. So this is representing this covering space. So we color the vertices of this graph, so you can think of it as like coloring the various walls here. And I claim that there's the group action on this cover, on these colorings of this covering space or the graph is amenable, is an invariant mean, or it's an invariant probability measure. Probability measure and invariant mean are essentially equivalent because it's a Radon measure. It's just it's a subset of a Cantor set. It's what this measure is telling you is that to each colored polyhedron, if you like, the faces of that polyhedron can be colored in various ways. And each of those colorings will have a certain weight associated to it. Namely, what's the probability that polyhedron gets colored in that particular way? And the sum of those probabilities for each of these polyhedra is 1. It's a probability measure.
What action is amenable?
There's a G. Oh, so I was just, yeah, so there's a probability measure on the space of these colorings which is invariant on the group action. It's actually invariant on the set of all automorphisms of the graph. So the way that this measure is constructed is the group action doesn't come in at all. It's just automatically invariant of the automorphisms because it's canonical. So,
so you're saying the fix it in where colorings are non-zero, and then that's a Cantor set, and then there's a measure on that which is invariant under all automorphisms of the graph. But the graph is an infinite graph.
It's an infinite graph, but it's finite valence.
Okay. And G is a subgroup of the automorphism group.
Yeah. It's this group of covering translations. Yeah. Okay, so so I just wanted to describe briefly how this lemma is proved. So the idea is, so I just said that, well, we can cover it with k+1 colors, but that breaks the symmetry because you have to choose which order you color them in. And there might be a proof that sort of makes that symmetric somehow, but I don't know how to do that. But
it also needed an ordering of the work.
Right. Yeah. So that's.
Oh, that's what you mean.
Yeah. If it's an amenable group, then it's automatic. Amenable groups always have an invariant measure. So what I do instead is I color with n colors, where n is way, way bigger than k, 1,000,000 or 1,000,000,000 or whatever you like. And I just color the vertices randomly. I flip a n-sided coin, color each vertex randomly. Now, the probability then that the endpoints of a given edge have the same color is 1 over n. So now I produce a k+1 coloring by using the ordering on the vertices. So I change the n coloring to an n-1 coloring if n is until I get down to k+1. So I get an n-1 coloring by, I look at all the vertices that are colored n, and I change that to the smallest unused color. Now there's every vertex has degree at most k, so the smallest, so it has at most k different colors used by its neighbors. So the smallest available color will be less than or equal to k+1 by the pigeonhole principle. So I get an n-1 coloring that way, and there's an invariant measure on that as well. There's a map from the n colorings to the n-1 colorings given by this map, and I just push forward the measure, and I get a measure that's on the n-1 colorings of the vertices. Now this is this is a coloring of the vertices, not of the graph, because it might violate the graph coloring condition. So then by induction, then you can produce a measure on the k+1 colorings of the vertices where the probability of coloring the endpoints of an edge E is the same color as 1 over n. now you take a weak star limit of these measures and obtain a G invariant measure now, which is supported on the colorings, because now the probability that the endpoints of an edge have the same color is 0, because it's a limit of this 1 over n. And that's the proof.
That there exists
In invariant coloring. So here's a random 1,000 coloring of this graph. And so I look at all the vertices colored 1,000. Well, I think the highest one here ends up being 998. So I change that guy to the lowest unused color. So this wall meets this one and this one. And neither of those, this is 387, that's 194. So I can color that with a 1. And then there was another 998 of this wall here. So I color that 1. Then I look for the next number. And I'm not sure which one it is, but oh, I guess it's this 953 here. And those guys are smaller, so I change that to a 1. So you iterate this process until, and in this case, so this guy, 919, gets colored with a 2. Now, technically, in order to do this, you'd have to know you'd have to go to like the 1,000 radius of this, because things can be, the numbers can change on nearby guys. And so this guy might have something else that was already labeled 2, and then you'd have to do something else. But I'm just demonstrating this on this finite portion, how it works. So, so this 919 gets changed to a 2 because it's the smallest unused color when there was already an edge that had 1 there. And then, so that gets changed to a 2. And 905 gets changed to 1 because these guys are bigger. And 861 gets changed to, now I can use 1 here because this guy is a 2. I use the smallest unused color. 827 gets changed to 1. 825 gets changed to 1. And then that's the, so actually this ends up being, I use only 3 colors in this example. But in general, you can always do this with k+1 colors. But actually to do this, I really have to go to a large section of the subgraph, radius 1,000, because if something is, if I have a chain of like 1,000 next to a 999, next to a 998, et cetera, it would go 1, 2, 3, 4, 5, and you might use more colors than you're expecting. So anyways, that's demonstrating how this, and then the probability that, that I have 2 guys adjacent. So these guys actually have the same color, even though they're adjacent. So this didn't work, but this is for any given edge, that's a very low probability that that'll happen. It's 1 in 1,000. So here's a coloring with 7 colors, for example. And so this gives me a hierarchy. I first cut along the edges labeled 1, whatever that color is, and then the edges labeled 2. And I get these colored polyhedra. So I get...
How do you go from the probability measure
to actual colors?
Oh, so the numbers are, those are the colors. So here I'm just using colors, but really these should be numbers.
But you have a probability measure on the space of colors.
Right.
You don't have a coloring yet.
So yeah, so let me, so you look at a color that's, say, in the support of the probability measure. Coloring that's, and, well, so for each polyhedron, any coloring of the walls or of the graph gives me a coloring of the faces of that polyhedron. And the measure on the space of colorings gives me a measure, what's the probability that this polyhedron will be colored, the faces will be colored in this way. So there's some probability attached to each of these colorings of a given polyhedron. If I take adjacent polyhedron, it'll have, for each coloring, it'll have some probability that its faces will be colored in this way. But if I look at the face that separates these 2 polyhedra, the probability that this guy will be colored green for this polyhedron is the same probability that this face will be colored green for this polyhedron, because they're adjacent and it's an invariant measure. So the probability measure then gives us a solution to some gluing equations that that I set up in the paper. The the variables of the gluing equations are these colored polyhedra, or actually what we need to do is what I call supercolor the polyhedra. So I'll explain what that means. What we want to do is we want to reverse engineer a hierarchy of a finite sheeted cover. So we have a finite hierarchy, but it's still non-compact, associated with this cover. And the probability measure extracts some sort of finiteness from this hierarchy, intuitively. So, okay, so the polyhedra are the stars of the vertices of this complex X, and they actually correspond to the stars of the vertices downstairs, unless there's torsion. And actually, I mean, all this works in the case of torsion, but I'll just ignore that for this. And then let F denote the facets of these polyhedra. And these are dual to the edges of the cube complex. So these are then the facets of the polyhedra P. So I just take one representative in each orbit. So in my example here, I have a polyhedron here, a polyhedron here. There'll only be 4 polyhedra because there was 4 hexagons in our original surface. And there'll be some number of facets. So here's an example of a facet. So we have P, Q, and a facet between them. Then the intersection between P and Q is this facet F. So I won't draw the other 2 polyhedra, which are just sort of mirror images of these guys, or reflections of those from the other sheet, yeah. Okay, so those are our polyhedra. And now for a given coloring, we get colorings of these faces of these polyhedra. So like this F is colored some color. Sorry, you can't really see the color that well. So now what I do is refine the K+1 coloring of the walls by a coloring of a neighborhood of size J, where J is the color of a vertex. So this is what, well, I guess Jeremy suggested calling this a supercoloring. And so here I look at a face, and I look at if it's colored. So these colors all correspond to some numbering. And let's say this, I think I colored this with 7 colors because it's a degree 6 graph. So I have, let's say F corresponds to the label 7. Then I have to look at the size 7 neighborhood in this graph, and I say now that I refine the coloring so that 2 colorings, or you get an equivalence class on these colorings so that of the face, so that 2 colorings of that face are equivalent if the colors of the neighborhood of radius 7 are equal. Bless you. So the facets get supercolored by their corresponding walls that they're in. So we refine the coloring of the walls by their supercolorings by the size neighborhood J in the crossing graph. The facets get supercolored by their corresponding walls, and the polyhedra will be supercolored by their facets. So 2 polyhedra with their corresponding supercolorings will be equivalent if all their facets have the same supercoloring. All the walls that are adjacent to that polyhedra. Now the point of this, why if it's labeled? Yeah, this is the picture here. So there's F here and F here. They're colored the same color, but we see that this wall here and this wall are oh whoops, sorry. These 2 guys are colored the same, but this wall here and this wall here are colored differently. You can't really see the color. I apologize. It's a light blue here.
Okay.
Yeah, it's something to do with the resolution of the pixels.
Which 2 guys and which 2 guys?
So here's my facet that I'm concentrating on, my sort of representative of this face. This wall here is colored yellow, and this wall here is colored light blue. So even though these have the same color, and even the neighboring, I've set up so the neighboring guys have the same colors, but if I go distance less than or equals 7 away, they're colored, these walls are colored differently. So these represent 2 different supercolorings. Now the reason that I do this, okay, so let me just give a brief explanation of why you need to refine the colorings this way. So when we reverse engineer the hierarchy is you cut along the walls labeled 1, then along the walls labeled 2, until you get to the walls labeled 7. When you reverse engineer it, you glue the walls together labeled 7 first. So you go in the opposite order. You want to guarantee that all the walls that cross through there match up, so you can glue the next level. That means that the walls that cross through that wall all have to have matching colors on either side. So what the supercoloring does is if you glue supercolored faces together at the 7th stage, then all the guys crossing through them will have to have the same color matching up, because the supercoloring guarantees all the walls crossing through it, which are adjacent, distance 1 array in the crossing graph, they'll match up. And then when you glue the 6 guys together, all the lower guys will...
6 neighborhoods will match up, right?
Their 6 neighborhoods will match up, and that means all the walls crossing through them will match up.
And 5.
And then 5, and et cetera. So that's why you color, the supercoloring is given by a neighborhood of size j has to, the colorings have to be the same. So that's the supercoloring of these walls. And this is sort of what this is kind of Thurston's reflection trick. It's kind of analogous to that, I would say. I mean, it's not exactly, but it's kind of analogous to that.
I still don't see how you get
From the probability measure to
Right.
actual color. You going to explain that?
So, yeah, so that's what I'll explain now. So the variables, so the gluing equations are, you have supercolored polyhedra. I described the supercolorings. And you, the gluing equations will say that for a given supercolored facet, the supercolorings of the polyhedra P, which induce the same supercoloring of F, must equal the supercolorings of Q, which induce the same supercoloring of F. So remember, we have these 2 polyhedra, P and Q. Now we take the supercolored polyhedra. It's just some copies of P and Q, but now with all these extra data attached, combinatorial data. And we have the supercolored face F. So we're going to attach a weight. So what the gluing equation is telling us, I'm going to take some number of copies of this polyhedron. I'm going to take some number of copies of this polyhedron with supercolored faces. What the gluing equations say is that the number of copies of this polyhedron P that induce a certain supercoloring of this F have to be match up with the number of copies of Q that induce that supercoloring of F, because I want to glue them together in pairs, and I have to make sure that the number on one side matches up with the number on the other side that induce the same color, the 7th level of the hierarchy, and then I can match them together. And then the supercoloring guarantees that when I glue those together, all the level 6 and lower guys that cross through here will also match up. So it's the fineness of the walls of this complex are allowing me to get these sort of matching conditions to work. So the gluing equations then are the supercolored polyhedra. So it's kind of like normal surfaces. So John, you're familiar with that, right? You have these quads in either tetrahedron and triangles, and a given triangle and quad has an edge in the corresponding triangle, and the number of quads or triangles that come in on one side with a given edge have to match up with the number on the other side. So it's kind of like that. So so I take these representatives, and then I get these polyhedral gluing equations, and everything is sort of G invariant. So for each face, I can it'll be contained in precisely 2 polyhedra up to the action of G, and then I have these weights on the supercolored polyhedra and the supercolored faces, and what the G invariant measure then gives us is it gives us some solution to these equations with non-zero weights, but there'll be some real numbers potentially, because it's just a probability measure. And then, but it's some linear equations with positive coefficients. So we can take an approximation by a rational solution, and then take non-negative weights, and then clear denominators and get an integral solution. And that gives us some number of copies of the supercolored polyhedra that satisfy the gluing equations. And that's our substrate for beginning our hierarchy. And that's our finite-sheeted covering space is actually then be made of some multiple number of these polyhedra with these particular supercolorings. So that's the 7th stage of our hierarchy, just a number of these polyhedra with all these faces colored.
Can you relate the measure to the
Gluing equations again? I mean,
Yeah. So
just abstractly? That's what you were asking.
I go measure colorings. The measure of the space of colorings.
right. So for a given colored polyhedron, we have a, this probability measure gives us some probability that this polyhedron is colored, all the faces are colored in this way. There will also be a probability that this polyhedron, all the faces will be colored this way. So I can look at all the probabilities of, or the colorings of this polyhedron that induce this color on this face, and all the colorings of this polyhedron that induce the coloring on this face. And the sum of those probabilities here that give this coloring will match up with the sum of the probabilities here that give this coloring. Now these give us exactly the solutions to the gluing equations. The gluing equations say that the number of colorings of this...
Compute probabilities that something happens.
Sure.
Okay.
I mean, I'm saying probability, it's just a measure.
Yeah, right.
But it's not negative.
And then what?
So then...
You can ask that they be equal or something?
That gives us a measure on the colorings of this polyhedron, and a measure on the colorings in this polyhedron. And the number that induced the color on this face, this purple color, whatever it is,
Induces the color on...
the probability that the colorings of this polyhedron induce this color on this face will equal the probability of the colorings of this polyhedron induce this coloring on this face.
Those are the equations.
Yeah, those are the equations. So you have, for each coloring, you have a variable of this polyhedron, you have a variable. For each coloring of this polyhedron, you have a variable. You have an equality that says that the colorings that induce this color 7 on this face F from this polyhedron P will equal the measure of the colorings on these colored polyhedra, the sum of the weights that give this color 7 on this face of this polyhedron. So it's a kind of matching condition.
You glue together certain things that have identical statistics relative to some set of questions. Like, what's the probability that this face has this color?
Right.
Will you eventually have an infinite set of equations?
No, it's a finite set of equations. I only take one representative for each orbit of polyhedron. So you could, in the case of hand of these, well, sorry, I'm not going to go all the way back, but in the case of the surface, you just have 4 polyhedra, and then you have some number of faces coming from the surface. There's only a finite number of those. For each face, there'll be an equation. For each colored face, supercolored face, there'll be an equation that says that the number of supercolored polyhedra on one side that induce that supercoloring of that face will equal the number of supercolored polyhedra on the other side that induce that supercoloring of that face. So this is a standard fact that if you have a linear equations over with rational coefficients, this gives you some polyhedral cone. If all the coefficients are non-negative, then you just go along a vertex of that polyhedral cone, and you get a solution with non-negative coefficients. And that's all you need to get. And that will have you can take some rational coefficients because it's defined by these rational hyperplanes. And so you get some integral solution to these equations.
So in the end, you get some. The denominator is n. That's capital N. So you'd have n copies of Q and n copies of P, and
right.
The number of, and they have the n different supercolorings, and the number they give a given supercoloring on F will be the same on the two sides. So you
that's right.
match them.
So then you can match them in pairs, and the supercoloring guarantees that when I glue this guy to this guy, this color and this color will match up.
But now you've got capital N copies of these that are glued.
Right, and you just glue them together however you like.
Yeah, so I see capital N sheets that I've glued together in pairs.
Right. So that's the second stage of our hierarchy, or the first stage was just this collection of supercolored polyhedra. Now the gluing equations say that the supercolored faces match up in pairs. So I start with the seventh, the guys colored with a 7 colored label, and I glue them together in pairs, but matching the supercoloring, so that you're not just going to glue 7 to 7 arbitrarily, because you need the color on one side to match up with the color on the other.
Right.
So if you glue supercolored guys, then the guys crossing through will have lower labels and less than 7, and will be matched up by the supercolored condition.
So you're just taking finite pieces of this infinite
That's right.
whatever. And you're taking in copies
Of each of those.
finite
Yeah.
pieces on this side and in copies of the finite pieces on that side.
Mhm.
I mean, these 7 neighborhoods overlap, right? So when you do the gluing,
Well, because of the coloring conditions, all the faces that are being glued together, the label 7 guys won't interfere with each other because they represent different colors of the crossing graph. And the crossing, so if 2 walls cross, then they have to have different colors. So they're not going to be the labels. The 7 labels are not going to interfere with each other because of the way things are set up. That they have to have different colors if they cross.
I'm just trying to understand what you're doing.
So
Trying to understand these properties that the colors match.
Right.
So you're taking, I mean, I have this F, and I have P and Q, and now you're taking some huge number of copies of P and Q that are given
Yep.
by this rational, the denominator is
Yep.
a rational solution.
Mhm.
And because the super colors, and you're taking these chunks of size 7 around Q, and a chunk of size 7 around P, is that what you're doing? And matching those together somehow?
No, so you're only matching those polyhedra together, but what the supercoloring does is it guarantees that when we glue up the later stages, everything will match up. So
I see, you just glue along the edge, but now you have this whole neighborhood which has got the coloring.
and this supercoloring is remembering how this whole neighborhood was colored.
Yeah.
So when we glue up the rest of the hierarchy, those guys are going to be glued up together in a way that's compatible at each stage. So
And the coloring?
you can extend the coloring, yeah, when you glue things together. And then you'll be able to use those to glue up the next part of the hierarchy, the other stages of the hierarchy.
Like you're painting. You
Yeah.
mix colors when you're painting.
Yeah, that's right, yeah.
So I guess I still don't understand what you're gluing together.
We glue together facets of the polyhedra that have the color number 7. I use 7 colors. All the pairs are 7, but you glue them together in a way that preserves the supercoloring and the gluing equation solution and guarantees that the supercolorings match up with each other. So you could just glue together all the faces willy-nilly, but that would give you some kind of branch covering of the surface. It doesn't give you a covering space. So this whole business is to guarantee that we get an actual covering and not a branch cover.
I don't understand what you're gluing together.
Yeah, let me, let's see. I have a, okay, here we go. I have another.
There's going to be faces of cubes, right? And they have to have the same color.
So I have some number of copies of P, and I have some number of copies of Q.
Okay.
And these guys each has a coloring, but the gluing equations keep track of the supercoloring. So I look at a given face, the face F, and I look at its supercolorings, and the gluing equations guarantee the number of polyhedra here that induce that supercoloring of F will match up with some polyhedra here that induce that supercoloring of F.
Now,
And so now I glue these together.
you've got these full, what we were calling 7 neighborhoods, but now they're probably 3 or 4 neighborhoods in this picture?
Well, so the supercoloring will keep track of how things are colored in some neighborhood, but the polyhedron itself is just by itself with its colors. But the equations keep track of more information combinatorially.
You have 6 copies of Q and 6 copies of P.
Yeah,
And you're somehow going to glue those 6 pairs together
that's right.
so the super colors match.
Yeah, so here's the gluing. So let's say black is 7. I glue these black faces together, and these are black faces here that I glue together from. So here is these black faces, and this guy matches with this guy matches with this guy. So I glue them together. Oh, sorry, I didn't draw the P prime ones. The P prime ones are then get glued along these edges, and then there'll be Q prime ones that match up here. So I didn't draw all the polyhedra because we're just imagining what can happen.
What's P prime?
Oh, there was actually 4 hexagons, and I didn't draw half of them. So these are the other half that I didn't draw before. And so the gluing equations guarantee that all these guys will match up. But the supercoloring guarantees that when I glue these P to Q, the hyperplanes crossing through here will match up. Not only that, but now when I glue the guys labeled 6 together in pairs, then all the guys crossing through guys labeled 6 will match up because their neighborhoods match. So
where did there are P's and Q's that haven't been glued together?
yeah, because they didn't have any faces labeled 7.
No, but in the middle row, in the middle row.
In the middle row?
Where you are. It seems
right.
Like 7 there.
The black is 7, so I've glued this guy a P to a P prime that I didn't. So here there's actually P's and P primes. I just didn't draw the P primes and Q primes.
But I thought we were gluing P's to Q's, and I was going to glue 7 P's to 6 Q's.
Right. So our surface. So remember, this is there's 2 copies of this.
Yeah, I understand.
Cover here. So I just didn't draw the P prime and Q prime polyhedra, and now I am drawing them, at least partly. So
you see P's and Q's glued together along the black.
P's get glued to Q's, P primes get glued to P's,
right.
and Q primes get glued to Q's.
There are P and Q's that are glued together along the black.
There's this one and this one. Yeah. There's 2 pairs. So this guy gets glued to that one, and that guy gets glued to that guy.
Because the other copies of F have a different, and the other copies have a different color.
And I haven't drawn the P. There's a P prime here with the same sort of color scheme, and a Q prime here with the same color scheme for each one of these that I didn't draw. And then those show up.
So if you have all these copies, you only glue the one color together.
So, yeah, whatever stage of the hierarchy you're at.
So if there were 7 and 2 of them gave black on each side, you would pair them up somehow.
That's right.
Okay. But in this case, only one gave only.
So I had this pair here,
black.
This pair, and these pairs that pair up with the guys on the other side,
okay.
P primes and Q primes. And then these guys didn't have the label, so they didn't get glued yet. Okay, so that's the second stage of our hierarchy. So, and some of these might if this had multiple black faces now, it might have gotten glued together, so we might have something that's relatively equivalent to a graph. So it's free fundamental group at this stage.
Can you remind me again why the automorphism is the graph? Preserve an invariant measure on the space and colorings?
Yeah. Because the scheme I gave for constructing the coloring was functorial.
Yeah.
So any automorphism of the graph will preserve that measure on the coloring because it didn't refer to because of the way that the graph was colored, the color was obtained, coloring was obtained.
You took n much larger than the graph.
Yeah.
That was the functorial. I forgot what the scheme was.
Yeah, the scheme was you just you flip a coin to color each edge.
Oh, and then you did the 1/n and on the limit.
Yeah.
Okay, right. But it does seem like if you have the highest valence occurs twice, don't you have to make a choice to which one you do first?
No, because so if 2 adjacent guys are labeled 1,000, you make those both for both of those you use the smallest available color. They might still be colored the same thing, but there's still only a probability of 1/1,000 that the color the same. They might get colored different, in which case you've improved the situation.
I see. So you go through, you look at all the maximal numbers, and you make those. For each one of those,
yeah, for all the guys labeled 1,000, you take the smallest available color that's not used by its neighbors.
Right, in the original.
Yeah, in the original coloring, yeah.
Okay.
And then you repeat that process with 999, 998.
Yeah, so that's completely.
And then you have to take the weak star limit, but that's some subsequence that.
You got to show us the next.
Yeah. So now, what might have happened at that stage is you might have actually glued things up in some. So the yellow guy has some non-trivial topology now. And now, by the supercoloring condition, we know that for each supercolored yellow guy here, there's a supercolored guy over here that matches it. But the problem is that we only know that they match up to finite sheeted covering spaces, because these, the way things are set up, these will all cover certain finite complexes that that came from. So these will be cover the some coloring of this space X, where all the faces are colored with yellow. But when we glue things together, we might have created a finite sheeted covering of that space. So now we have to pair these up. So what the supercoloring guarantees is that the two sides will have consistently supercolored walls, and therefore there's a finite sheeted cover of the wall representing that given coloring in X. That's not, I'm lying slightly there. You might actually have to, the coloring might have certain automorphisms that you have to quotient by, but I'm brushing that under the rug here. I mean, it's a little more technical than what I'm saying. But what happens is that the supercolored guy that you get at this stage will cover a corresponding supercoloring of the hierarchy I had for this infinite covering space. And again, it's there's a little caveat there. It's up to some finite index, but you have to take a certain quotient that respects the symmetries of the coloring. Now, the Malnormal special quotient theorem is invoked again here and allow us to pass to a covering space of this complex where these things actually match up. So here's again where malnormality comes in a strong way. I said that the colorings made everything acylindrical, and the big advance that Haken and Wise made in their Annals paper is that they showed that if you have, they showed that if you have this sort of situation where you have these two groups and you're trying to glue them together, then you can glue together finite covering spaces along this malnormal subgroup. So this is another sort of black box that I'm invoking here.
So what happens here in this picture,
So,
you have the trivial two-sheeted cover on the left and the unwrapping
Two-sheeted cover on the right. Is that what happens?
yeah, so here's a two-fold cover, and here's two-sheeted trivial cover. So now I can just pass to a cover two copies of this guy, and then I take the two-fold cover, yeah, like you just said, yeah. And now I can match them together. But there's this highly non-trivial theorem, essentially of Haken and Wise, although I apply the Malnormal special quotient theorem with a little work. I mean, Haken and Wise didn't prove exactly what I needed, but it follows from Wise's work that you can find a covering space now where these guys match up as covers of the corresponding wall that we had in the covering space. And now you proceed by induction. So now you want to glue up the guys labeled 5s. And again, those guys only match up to finite index. But you again, everything is malnormal. You can use the Malnormal special quotient theorem to find a cover where things match up. The way that the Malnormal special quotient theorem here is used is that these are virtually special cube complexes, and these are subgroups. So the Malnormal special quotient theorem says I can kill some power of this guy, some power of this guy, some power of this guy, that's a virtually special quotient, as long as that power is some multiple of some number that's given by the theorem. So I make that number to be the least common multiple of the number I kill a power which is the least common multiple of these numbers given by that theorem. And that quotient will be residually finite. So I can take a finite sheeted cover. So there's a fact that if you have a residually finite group and you have an element of finite order, there's a finite index subgroup where that element is, or any of its powers are not contained in that subgroup. You just separate it from the identity. So you can pass to a cover where this element is trivial, and that means you've unwrapped this by some common power that allows you to get this covering space. So that's how the Malnormal special quotient theorem is used.
Any power be also outside the subgroup?
So I take an element of finite order. It has finitely many powers.
Oh.
I separate each of those powers from the identity. And now that subgroup and I even take a normal subgroup that has that property by passing to the normal core. Then that subgroup will have the property that all the powers of that element are not contained in that. And so when you pass to that covering space, these guys will have a common cover that's whatever that power is that you killed. So that's how the Malnormal special quotient theorem is used to match these up. And it's a highly non-trivial theorem. And so then you repeat this process. So now we take V6, we pass to this covering space, now we match, everything matches up in supercoloring. So again, when you want to glue up things in pairs in the next stage, everything will have matched up. When you try to glue them together in pairs, there'll be some balanced matching, but they'll only match up the find index again. So then you keep gluing together. So you obtain the I stage of the hierarchy from the I plus first stage by first passing a covering space in which the boundary pattern matches up in pairs, and then and preserving the supercoloring. And then, so this requires applying the Malnormal special quotient theorem. And finally, you get to the cube complex V naught, which has no boundary pattern and represents a finite-sheeted covering space of X. So we've sort of we've reverse engineered this hierarchy. At each stage, we pass to a covering space where we can glue up the next stage of the hierarchy, and then pass to a covering space again and glue it up. And the supercoloring somehow guarantees that everything will match up in pairs. Okay, and then one more application of Wise's theorem then gives us a cover which is special, because now we have this Malnormal. We've reverse engineered a quasi-convex hierarchy, and Wise proved that quasi-convex hierarchies are virtually special. So that's the summary of the proof of the theorem. So I've invoked, all of Donnie Wise's work, especially this Malnormal special quotient theorem. It's a good, 120 pages or more of math. So now Jason Manning and Daniel Groves and I have another proof of this Malnormal special quotient theorem, which we're just finishing off the manuscript. It's almost done, just fixing a few things, but that should be available, I think, pretty soon, like hopefully next week. And that's the key thing from Wise's work that I use. So it's a non-trivial theorem, because generally when you take a residually finite group, you take a quotient of a residually finite group, most likely it's not going to be residually finite. So so his theorem is sort of giving this category of groups where you can take certain controlled quotients and get those to be residually finite. It's also a little surprising that the Wise is trying to prove this Baumschlag conjecture that if you take a one-relator group with torsion, that it's residually finite. So this Malnormal special quotient theorem says that Baumschlag's conjecture is true if you take certain powers of, take an element to some high enough power, then you'll get a residually finite quotient. But somehow kill a high power of element in a free group, then you get there's a quotient that's going to be virtually special. But he can use the power of this theorem in some complicated inductive argument to the quasi-convex hierarchy to get an actual, prove Baumschlag's conjecture without any condition, just that it's torsion. You need to have torsion because, for example, there's Baumschlag-Solitar groups that are not residually finite. So you need some kind of hyperbolicity for these things to work. And I would say that, where you can see the sort of hyperbolicity coming in one aspect is this malnormality, that if you want to glue things together, you want things to be malnormal. So one thing that fails, like if you tried to do this with the Berger-Moses kind of complexes, is that you wouldn't be able to get the walls to be acylindrical, because there's lots of parallel cycles between them, because it's basically looks like a product of free groups. And that's not allowing you to, so that when you want to match things up here, if this had cylinders go to some other boundary component, if I took a covering one boundary component, it would force certain covers of the other ones, loops would have to match up. And then that's much harder to sort of arrange. So that's, in some sense, when the malnormality comes in. When these guys are also all independent, then you can pass to covers which are sort of independent. That's Haken and Wise's key contribution. And that's highly non-trivial to prove. Okay, so that's kind of a summary of the proof of Wise's conjecture. And if you like, I could say more words about the proof of the Malnormal special quotient theorem, or the proof of Wise's theorems, what he's proved, which, as I say, goes into this, but it's quite complicated as well. Right.
Malnormal, is this some sort of relative non-existence of relative annuli? Is that what it is?
Malnormality, yeah. So it's like an acylindrical condition. So if you take a embedded totally geodesic surface in a hyperbolic manifold, then that's a malnormal subgroup. So it's like an acylindrical. If you take a geodesic in a hyperbolic manifold, that's also malnormal. If you take an immersed geodesic surface in a hyperbolic manifold, free manifold, it'll cross itself. And the intersection, that you get a self-intersection, which is a closed loop. That itself might be immersed. It might have like triple points or whatever. But those closed loops will represent that subgroup is not malnormal because it's intersecting itself non-trivially in a conjugate, which is that cyclic group. The way that the weak separation happens is what we do is, let's say we have a hyperbolic manifold that's immersed totally geodesic surface. So it intersects some conjugate, conjugate of itself and of the fundamental group in this circle. That circle is malnormal. So we kill some power of that so that the surface group, that geodesic surface group in that quotient is virtually special. So the Malnormal special quotient theorem allows us to kill some power of that element that's making it not malnormal. We kill a power of that and get a quotient in which that surface group becomes malnormal. It has has virtually special image in the quotient. Now the image in that quotient will not be now malnormal, but it's what's called almost malnormal. So almost malnormal means that if you intersect with the conjugate, the intersections are finite. And that's sort of like good enough for what you need. So now in the image, you get an almost malnormal image of that surface group. And now you can apply the Malnormal special quotient theorem. So the Malnormal special quotient theorem actually applies to these groups that are sorry. Anyways, we can now kill the image of that surface group in that quotient, or kill some finite subgroup of that using the residual finiteness and using relative hyperbolicity to guarantee that the quotient is non-trivial. So the weak separation argument is applied by an inductive argument on a quasi-convex subgroup. So quasi-convex subgroups are not necessarily malnormal, but it turns out they have only finitely many of its conjugates can intersect non-trivially. Think about a quasi-Fuchsian group in a hyperbolic manifold. You look it might intersect some conjugate, but that means that the convex holes will overlap, and you intersect those convex holes and you get something that's simpler. You can only do that finitely many times because the convex hole is compact. It can only intersect itself with some bounded multiplicity. So eventually you'll get down to something that is malnormal. And then those are the things that you kill first. And then you kill the next stage using the Malnormal special quotient theorem and iterate like that. So that's how the weak separation is proved using Malnormal special quotient theorem. The Malnormal special quotient theorem is proved by, so what you do is, okay, so we had this hyperbolic group in this element H inside of that hyperbolic group. It's more generally, you can have a collection of malnormal subgroups. So let's just consider the cyclic case. So that group is hyperbolic relative to that subgroup. There's a notion of relative hyperbolicity introduced by Bowditch and Farb and some other people that it's like a cusp of a hyperbolic cusp manifold is hyperbolic relative to that cusp. So what it corresponds to is if you took the Cayley graph of that group and you attached a horocycle onto each copy of the cosets of that cyclic subgroup, the resulting space that you get, metric space that you get, is still delta hyperbolic for some delta. That's essentially equivalent to being to being hyperbolic relative to that subgroup. Why is malnormality important? Well,
The subgroup is always a Z.
yeah, so I'm considering the case of Z. So it's more general than that, but just for the sake of argument or explanation.
So
What you do?
So a relatively hyperbolic group means that you take, it's hyperbolic relative to a subgroup if you attach a horoball. So you take the Cayley graph of that subgroup and sort of take the horoball associated with that, which just means you take that graph crossed with R, but with an exponentially decreasing size, just like a horoball. And if that resulting, so you attach this onto all the cosets of that subgroup, if that resulting space is delta hyperbolic, then it's said to be hyperbolic relative to that subgroup. So if you did this for a hyperbolic cusp manifold, well, the compact model of that manifold is just chop off the cusp. And that's not delta hyperbolic because it has these flats in there. But if we could put the cusp back in, then we do get something that's hyperbolic. And so a relatively hyperbolic group is like that. But you want it to be malnormal because if I had two cosets that intersected in some infinite cyclic group, if I attach two horoballs under there, effectively what I've done is I've taken a horoball and I've doubled it. And that's not hyperbolic because it's got this concentrated positive curvature along the horoball. Like take two pseudospheres and glue them together. Take the universal cover of that. That's not hyperbolic. So that's why malnormality is important. So Bowditch proved that a subgroup of a hyperbolic group, the group is hyperbolic relative to a subgroup if and only if that subgroup is malnormal or almost malnormal and quasi-convex. So we can apply this, it's kind of funny, but we can apply this relatively hyperbolic Dane filling techniques to this hyperbolic group relative to these malnormal subgroups. So our proof of the Malnormal special quotient theorem, what we do is we have this hierarchy and we sort of augment the hierarchy by these peripheral subgroups. So you pass to a covering space where you can take a combination of these hyperplanes with the corresponding cyclic subgroups and get a malnormal hierarchy of a cover that has the property that these cyclic subgroups, whenever you take your amalgamated products of your hierarchy of this cover, the cyclic subgroups are always conjugate into one side or the other. So they're sort of preserved under the combinations. And that means that when we do a Dane filling on that subgroup, kill a power of that element, then in the quotient, it'll still have that same amalgamated product structure because because the cyclic subgroup in each amalgamating subgroup lies on one side or the other. So the idea of the proof then is you pass to a covering space where you have a hierarchy that preserves these cyclic subgroups in each stage of the hierarchy. So you have this iterated amalgamated products and H and N extensions. And at each stage, each cyclic group, each conjugate of a cyclic group, it lies in one vertex group or another of your amalgamation. Or it could lie in the amalgamating edge subgroup. And then what happens is that hierarchy, when you kill this powers of an element, the quotient, that hierarchy will persist in the quotient. And so it will have a malnormal or almost malnormal hierarchy. And then Wise's theorem implies that it's virtually special. So I should say this is Wise and Shu and Wise together. So before Wise proved that a quasi-convex hierarchy is virtually special, he proved that if there's a malnormal quasi-convex hierarchy, that those are virtually special. And that's a combination of work with Hagen and with Shu, Tim Shu. So that's a whole other 60 pages of math and malnormality is crucial in those kind of arguments. So anyways, that's sort of a summary of Wise's work.
Is there any echo of these ideas in Papikariacopolis' 57 paper? Sphere theorem? Because he also removes self-intersections by taking coverage, but I never looked at those arguments.
Yeah. There's cut and paste. Yeah, Papikariacopolis' theorem. There's a point. It's in some sense it's a sort of complicated cut and paste.
I think in the sphere theorem you really have to look at coverage, and the others, things on the loop theorem, you don't. You can just.
No, you. Well, okay, yeah. There's more modern proofs like to do Johansen that use hierarchies and. But the Papikariacopolis' theorem, the way it goes, you take this immersed disk or immersed sphere, and then you take you assume that you take a neighborhood of it. If some boundary component is a sphere, then and it's essential, then you're done. So you assume it's not, and then there's going to be a non-trivial homology, and so a non-trivial covering space of the image. And that sphere or disk will lift to that cover and will have fewer intersections. So that is maybe, somewhat analogous to this covering space that I'm taking, which gets rid of the intersections of the submerged surface. But I'm taking this infinite cover. But yeah, that maybe has some analogies. Yeah.
Are you leaving tonight?
No, I'm leaving tomorrow morning. Yeah.
Who's feeding you?
Oh, I guess you're going to. Okay. Well, that's thanks.
I was a default Schwartz.
Oh, default was.
Pork?
I've.
Come too? No. I've got family obligations.
Yeah.
Sick.
Sick family. Yeah, you should.
I gotta go.
Get home. Yeah. Well, I appreciate all your questions and.
All right.